What did we do last time? Where are we at in this whole story? Talk to me, especially if I haven't heard from you in a while. Yeah, Earth's crust. Yes, we did. And Earth. We started Earth in general. This is true. What's interesting about Earth's crust? What did we talk about?
Not that deep.
What's that?
It's like pretty thin.
It is pretty thin. That is true. There's what else? And up back here. Remind me your name again. I always forget. Ellie?
Talked a lot about that.
What was that?
Like
Tectonic plates. Yes, yes. All right. What about tectonic plates? Yeah, Ezra.
We talked about the theories about what could have caused the continents to shift apart.
We did. We ended on that, and so we can start there once we get going. What else? Yeah.
I was going to mention how, like Wegener proposed this idea of continental drift, but didn't have the tectonic plates to back up his theory at the time. And then we talked about how Carey said that he thinks, or that he thought, that the Earth expanded, and that's how the continents stretched out.
Yeah, both of them are kind of far out fringy dudes at the time too. Uh, neither idea was particularly popular. And then this subduction thing and this mantle convection gave Wegener a mechanism. Carey never did have a mechanism at all. And I started to kind of hint at one that might have saved Carey, but we stopped there. Yeah.
What was the name of that dinosaur, the big bird one?
Oh, the Quetzalcoatl. Yeah, I told that story too. I forgot about that. Yeah, that's pretty far out. Yeah, it's a weird one. So I should have pulled up some more info on that. There's this thing you can look up called Tenake's flight diagram, which basically plots the size of animals versus I believe their wingspan, if I'm not mistaken. And everything fits on it, except for some of these dinosaur. Well, they're not technically dinosaurs. I'm not sure why. I'm not a dinosaurologist or whatever, but yeah,
I know why. Because
you know why.
was all
Of course you do.
technically. There were three sweet animals or creatures
Yeah.
on the planet
Okay.
after an extinction event, and only one of them evolved into the dinosaurs.
Okay.
So, no, but the other two, anything that evolved from the other two, are not dinosaurs.
But they're kind of dinosaur-like. They're big.
Yeah.
Yeah. Okay. Fair enough. It's not technically a dinosaur, but of that same era. Um, yeah, it's kind of interesting. So let's get some more thoughts on the table.
Left on the idea of the Earth's atmosphere and its um, part in possibly changing the Earth's look or the place, not so the lack of like atmosphere, and how that would also explain the size of the cosmos.
Maybe. So my kind of what I was hinting. Does anybody know what I was trying to sort of hint at here? Because this is an idea I'm gonna keep building out for you guys. What the heck? Why would I bring up the thick atmosphere and the plates and all of this? Where was I going? Somebody who hasn't spoken yet. Yeah. All right, we'll come back to you. Yeah, Tammy.
Buoyancy, because the thickness of the air allowed for more buoyancy for dinosaurs, but also the land walking dinosaurs, because their bone density shouldn't have worked with their mass.
That is true. So what could that possibly have to do with the plates and stuff like that? Yeah, in the back.
Just the expanding Earth theory.
Yeah, so fill that out for me.
Well, we were talking, I don't know if this is like where you're thinking, but last class you said something about uncompressed density,
Yeah.
which is like the density of a planet without the atmosphere on it, or I don't know.
Yeah, that part's a little sketchier. I actually just came across that diagram, but you're in the right direction.
But if we're saying that the atmosphere thinned out over time, could it be that the Earth expanded with less atmospheric pressure onto it?
So I've actually done that calculation before, and the answer is yes, but it would have been an enormous atmosphere, like the size of a mini Neptune, something a little bit smaller than a Neptune.
Is that what you were talking about in your podcast with Don Petit?
Yeah,
I
yeah.
was just listening to that.
Oh, cool. That's an old one. Yeah, nice. I'm glad you checked that out. So Don, I mean, It's a super heretical idea, so we all sort of talk around it because nobody wants to come out and totally say it. It's becoming less of a heretical idea because people are publishing in the astrophysical journals this mechanism that Neptune's, and we'll get to this when we get to Neptune's. I think this is when we'll really look at the papers. There's this idea that Neptunes do, we actually see them when they get too close to their stars sometimes, that their atmospheres are blowing off really, really fast. So you can imagine if you just took like a snowball and put it next to the sun, right? It's going to blow away. Now, the atmosphere of Neptunes, as this happens, a lot of people are starting to recognize that what would result from that is something that looks like one of the most common types of planets in the universe, which is called a super Earth, which is a bit bigger than ours. It might be true that it makes normal sized Earth too, or just that normal sized Earths are really hard to see because they're tiny. So anything big is going to be easiest for us to see at a distance is the problem. So we have a bit of a sampling bias towards big things. So yeah, so that was kind of my idea. I was thinking if Carey had thought of this in his day, perhaps perhaps this would be the textbook picture. That doesn't mean that it's right at all, but I do think that it would have saved him. And maybe it is right, but I think that anytime that you're talking about things that happened billions of years ago, you're in a deep theoretical space where any new little thing that you learn could radically change the story that you tell. Yeah.
I think it would be, well, first off, the uncompressed mass, if I remember, was just the mass of the planet, or the density of the planet,
Density, yeah.
if it was not, if of just the materials, regardless of gravitational pressure,
That's right.
condensing that mass.
That's right.
So
or whatever pressures, yeah.
happening.
Yeah.
At least from where I'm sitting, I feel like there's too much evidence for plate tectonics existence to entirely disregard them and say that, oh, well, it was just that it expanded. But I also
Which ones in particular?
Just all of the fault line, all of the.
Well, they both involve the fault. They both would utilize the same fault lines.
Not in the same mechanism. That's the problem. Now I don't. Now in plate tectonics doesn't necessarily. When I was learning about plate tectonics, there was already. It was already pointed out to me in the textbook that I was reading, which was a 2024 textbook, that um, the convection theory was already sort of in dispute because it didn't line up with where magma was actually going up. But there's probably a different explanation, but that process is still, that we observe is still happening with the plates.
Yeah, it's kind of weird. I have a hard time with it.
Neptune makes a lot of sense as well.
Yeah.
Both could be true.
I don't know what's true. I have a hard time with the Pangea thingy on one side of the world, in particular just based on the vector maps of which directions. So you guys can Google this right now if you have a computer. You can see the vector maps of where the plates are moving, and they're not really moving in the way predicted by this Pangea thingy, right? They're not like all gravitating away from each other. Some of them are moving down and away. They're not moving away from the seafloor spreading events, which was part of the continental drift theory. It's pretty bad, actually. So I don't know. I really don't know. I do know that we have a really weird planet that's doing this actively, and we can observe certainly the plates are moving, which is interesting. Let me throw another piece of evidence that actually makes this theory a little bit more appealing to me as well, which is the age of the oceanic crust.
Yeah, it's really young.
It's really quite interesting, right? So again, according to the standard continental drift Wegener plate tectonics thing, right? Again, I think that both models are plate tectonic. I call one like expansion tectonics versus maybe continental drift or something like that.
That makes sense.
But this is not, if this is what's happening, and the basic mechanism of continental drift is that there's these seafloor spreading events that are pushing the plates away from each other, that's not actually the motion that wood that's really like moving these continents apart from one another in some sense. Like if you look at the age of these floors, these are really young for the most part. This is what, only 10 million years old for the most part. And, you know, some of the oldest parts are maybe 100 million years or something like that.
Yeah,
It's
it's
sort of,
basalt constantly gets regurgitated and so it subducts and then comes back up constant, which is why it's only really basalt. That's
well, the
what we
sub,
see
yeah.
constantly happen in the ocean is that it's anytime that oceanic crust hits continental, continental is much more dense, much older, and thus it just subducts under it and then flows back up.
Yeah, so it's all very, a lot of little missing pieces. I don't know. I mean, again, I think my goal here is more to just expose you to something you might not have heard of before. You can read more about both of these and see which one. Obviously, one has been more popular in the 20th century than the other, but it's quite interesting, and I wouldn't be surprised to see a reversal in the way people in the popularity of these, particularly as we come to understand these Neptune transitions. So I don't know. I mean, yeah, I really just don't know. This is really cool though. I mean, you know, for Carey's model, you can certainly imagine that you had some sort of shell that's really, really stiff, that's kind of like an eggshell, right? And as soon as the eggshell ruptures, then if there is this elastic expansion, maybe even just like some sort of thermal expansion, or I don't know no, that wouldn't make sense. If it did expand, maybe it happens quite quickly, maybe over the course of just a few 100 million years or something like that. And yeah, it would explain a lot of weird things about the dinosaurs, and perhaps explain this weird business about the overlapping fossil structures. And you know, maybe it would do that explanation better than the Pangea thingy on one side of the Earth flying apart from itself. Um, I don't know. It's just kind of interesting. Thoughts, concerns? Yeah, sir.
I'm just kind of confused about the heat map
Mm-mm.
that you showed us.
Yeah.
It,
This one?
not this one, but
Okay.
that shows the hot spots coming up from under the.
Oh yeah, the mantle plumes.
I'm still just really confused about that versus this and what
Oh yeah.
kind of.
That's a great question. I wish I could overlay them, actually. That would maybe be a lot easier. So the original continental drift plate tectonics theory had the upwelling plumes underneath these rifts, right? So basically, you would have all this magma pushing up from the surface at these rifts and spreading the plates apart. But when they finally went around to mapping these upwelling regions, they have no correspondence to the rifts whatsoever. So for me, it seems to imply these are not actually upwelling events that are spreading the plates apart. It seems like more of a stretching open of the ocean floor than anything else. So, you know, in Carey's model, these would literally be the fresh innards of the Earth that are being opened up as the whole thing is expanding. And the old continental crust stuff was kind of what was on top originally, before like the fresh stuff was exposed to the ocean. And maybe there's a means for the creation of a lot of that ocean water as well, because we know there's tons of water locked up inside the minerals underground too, that exists in that kind of magmatic form right now, right? But I don't know. Yeah, again, super cutting edge, weird stuff. There's a number of people that will walk on the edge of these kind of realizations, but it just hasn't reached some sort of safe tipping point for most academics, so you don't hear about it. But yeah, it's kind of cool. Thoughts? Anybody else? All right. Should we keep going? I wanted to talk about the core today. Actually, I'm going to talk about two things today. I want to talk about the core, and I want to talk about the atmosphere. So, the core. If we're going to understand the most interesting thing about the core, needless to say, from all of those seismic studies where they did the different waves and the stiffness mapping and so forth, there's something really rigid and solid-like at the core. There's something a bit liquid-like and also differentiated from the mantle region above it. But what's most fascinating is that we attribute that incredible magnetic shield that we have to the core. And so that requires us to understand how magnets work, unfortunately, because I think that at least half the class is sick of atoms and probably wishes we didn't have to do this. Sadly, this is the last time I think that we'll have to deal with atomic level stuff. But I don't think that we can make sense of magnetism if we don't understand, at least have a picture of how atoms can do this magic stuff that that we're so familiar with and is so important to our survival. So, just so you guys are on the same page, the Earth's magnetic field is quite interesting. It periodically reverses. Now, the way that we know that is honestly by looking at different regions in the layering structure of the Earth that have basically iron atoms whose polarity has been reversed periodically, like every, I don't know, 700,000 years or so. Let's say million, just to make it even. So the polarity, the North Pole versus the South Pole, it changes sometimes. And, it's pretty obvious there's a magnetic field if you've ever used a compass or something like that. Birds use it to navigate. It's a really, really useful feature. And it screens a lot of the nasty solar wind stuff that we're going to briefly talk about here in a minute. But how does this work? How in the world does the Earth have a giant magnet in it? How do magnets work in general? Particularly this kind, because generally the way that people understand that this magnet works has to do with a dynamo, which is really closely related to a solenoid. In other words, an electromagnet. And so it would be good for us to understand that a little bit. So, previously when we were talking about light, I built you out a model of the atom, which was pretty simple. But it essentially had a surface motion that could reflect this concept of spin 1/2. Now, spin turns out to be extremely important in magnetism as well. It actually tells us the direction that the magnetic field is oriented. And what is a magnetic field, by the way? It's just a map of magnetic effects, right? So it's kind of like a three-dimensional model that tells you the direction and how strong your magnetic effect is going to be at any point, all right? So if we take this model of spin that I gave you guys before, basically the atom, let's just imagine the surface of the atom actually has some sort of material, it's in motion, it's basically rotating around the equator, but it's also involuting into the atom as well. So it gives us this really nice 720-degree symmetry. And then, I also have explained that it's reasonable to expect that the surface of the atom isn't just this nice shell, it's actually quite extended, right? So this allows us to convey effects to our neighboring atoms that aren't exactly touching us. All right, let's keep that in mind. And let's draw first a really, really simple wire. So like the simplest wire that we can possibly imagine. It's just going to be made out of a single hydrogen stacked on top of another hydrogen stacked on top of another one. So I'll just draw a couple of these, a little string of pearls or something. Now, let's just say that electricity is traveling through this wire, and you can imagine it's atoms all the way down, all right? So in this case, all of the atoms are kind of turning together as one entity, right? So, but they also have surface motion that's flowing in their top and out their bottom. So in some sense, each atom is sort of rotating into the board like this, and the whole column is sort of rotating around in a circle like this. Does that make sense? Sort of twisting like as a column, all right? Now, this follows the same spin geometry that I drew for you guys before. Now, what if I take this wire and I curl it, I stack it, like I curl it into a coil like this, right? This is basically the simple principle of a solenoid. Well, what you notice is that now all of a sudden, this motion, this same motion, let's say, best way to draw this. Say it's curling into the board or something, doesn't really matter. But let's say it's curling into the board over here. All right? What we've done is we've aligned the equators of all of these atoms like this. So they're all curling in the same way. All right? Sorry, I'm trying to make sure that I'm getting my perspective right. Yeah. Does that make sense? The result of that is that all of these atomic surfaces are all turning together like this. They're all wrapping around the entire coil and into the center of the coil. The result of that is that the equatorial motion, which is the magnetic effect, is synergizing in the coil when you coil that wire up. Basically, all the equators of the atoms are all moving together really nicely in a line like that. And the effect is that the surfaces are synergizing in this coil. And the harder we drive a current through this wire, the stronger that magnetic effect is going to get. Remember, the surfaces of these atoms are extended. I think of them as kind of furry, right? So this motion is extended at some distance to its neighbors as well, all right? So this is a basic floor plan for an electromagnet. You're driving a coil through this. Now, there's another piece of this puzzle, which is really fantastic, which is that if you want to make a really strong electromagnet, you keep the currents the same, everything's the same, the number of loops is the same. What do? You stick a big piece of nickel or iron in the center of the electromagnet. And what happens? Well, it's kind of like, have you guys ever magnetized a paperclip before or something? You just drag it across a magnet, right? So iron and nickel have this very strange ability. They're, of course, way more complicated than these simple 1s shell atoms that I've shown you. But they have the ability for some of their outer surface to take on the polarization that's given to it by magnets, right? So they're magnetizable is probably the easiest way to think about it. So what happens is when you stick a big chunk of iron or nickel in the center of an electromagnet, it takes on the pattern of this motion that's been imprinted on it from the electromagnet. And it actually reinforces it because now all of its atoms are doing the same sort of motion as the current that's driving it. And what's really interesting is when you turn off the current going into the loop, it still maintains that same motion. It's almost like a flywheel. You guys know what like flywheels are? They have these really crazy things. There's these flywheel factories in San Francisco. Have you seen these things? So there's like a company who had this kind of diabolical idea that if they just built a bunch of these big, heavy, almost like millstones, and they used a bunch of electricity during the day. Sorry, think about this. Yeah, everybody wants power during the day, right? So they use at night. They run an electric motor and they get these big, heavy wheels spinning. And then they sell that electricity as they turn it the other way and allow it to drive power into a generator so they can sell the electricity back to the city during the day when electricity costs more because everybody's trying to use the power grid, right? Does that make sense? It's like a motion storage medium, basically. You spin something really heavy, it keeps spinning indefinitely, not indefinitely, the friction will slow it down eventually. But you can use that momentum, you store that momentum so you can just use it to drive a generator. Yeah.
If you've ever used like, is it like those wind up cars? Like you wind it up, and then when you let go, it reverses.
I think those are spring based, but it's yeah.
Similar to that.
It's a storage mechanism. Yeah, it's a storage mechanism. So I think that that's the way that the iron cores work as well. Is they sort of store that motion that gets imprinted on them by the current generation. So the reason that I show you all this is because basically the same thing is thought to be happening. Inside of the. So here's our coil system drawn a bit better than my board drawing, but the same thing is thought really to be happening both inside of the sun for the most part, but let's just stick with here with the Earth. It's a bit more complicated in the sun, it's a bit messier. Basically what we have is we have a turning Earth, right? We've got convection currents. Again, convection's huge part of the story here. Convection currents, you know, whether or not they have anything to do with this, or that they're patterned to the crust in the proper way, doesn't change the fact that you're going to get these eddies from basically spinning a can of soup around like this. And the result of that is that these are really conductive materials. You get some sort of charging just due to friction, much like, you know, if you rub the balloon on your hair or something like that, right? This is called triboelectricity, which is really, honestly, can be easily thought of as just, you know, grinding those surfaces of those atoms kind of just like gears, just spinning them up, right? Spooling them up. The result is that you essentially drive something that's akin to an electromagnet, a solenoid, or a series of solenoids inside of the mantle, the liquid part, the inner core, the outer core deep in the mantle. And that the solid inner core sort of maintains that. So then, first of all, is this making sense? Okay, good. So then the question becomes, why does the pole reverse on the magnet every once in a while? Yeah.
Is it because the internal slosh around? And so then it's
I think that it's kind of a trick question. I don't expect you guys to know this because it's a pretty weird phenomenon. So I'll tell you a story. Something really crazy happened. So back in the 1970s, when there was the big space race going on, Cold War and everything, the Soviets discovered something that they kept secret for 10 years while they were in outer space. Has anybody heard this story? It's quite interesting. So they basically had this weird experience where, you guys know what a wing nut is? Like one of those tight things you tighten down a screw with. It has little like ears on it, kind of built-in screwdriver, basically. Somebody was untightening one on one of their early space stations, and was untightening this thing, and it popped off, and he was like, "Oh, that's cool." It just kind of kept spinning, and he was watching it. Then all of a sudden, it did the strangest thing. It completely inverted its spin pattern and started spinning it flipped over, like did a tumble, a somersault, and then effectively was spinning the opposite direction. And then it kept going, and then it did the same thing, and it inverted. And this is really, really quite interesting. And so, now why did the Soviets keep this secret for 10 years?
because they try to keep everything secret.
Well, fair enough, fair enough. They weren't in the business of telling people about things. But no, they were really worried about it, actually, it turns out. So I read an interview with one of the original scientists working on this, and he was actually quite concerned. Why were they concerned about it?
Because it didn't make sense to them.
What are you going to say, Max?
To say they couldn't explain it.
They were worried that the whole Earth would do that, actually. They thought, oh man, if this is just a thing that objects spinning in space do, that maybe the whole Earth's going to turn over at some point. And that's what's causing all of this stuff to happen. Yeah.
Isn't it thought that the flipping of the poles would cause like the collapse of our society?
There's some doomsdayers who would have you believe that for sure. But hold on.
What would it exactly do to like technology?
I don't know. Let's play with that in a second. I think that's worth considering, but I want to make sure that we understand why I'm pointing this out to you guys. So anyways, they did a bunch of people finally calculated that this wouldn't happen. But the reason that it wouldn't happen had to do with the fact that the reason that it happened with the wing nut is because there's a slight mass imbalance on the wing nut. One side's heavier than the other. And if you want to read more about this in math, this is actually called the intermediate axis theorem. So you can do it with a tennis racket too. It actually kind of does the same thing where its pole flips as well. When you throw a tennis racket up in the air, it'll actually spin over and come back the other way. This is like a huge math problem. Yeah, mathematician.
The phone as well.
You can do it with a phone, yeah.
Over in that orientation.
There you go.
Doesn't work.
And this is some like really gnarly math associated with this and trying to make sense of it. But even the slightest imbalance basically on a sphere will lead to it eventually doing this. And there's some periodicity to it. It'll spin properly for a while. The slight imbalance gets to be enough that it wobbles. And then as soon as it reaches some tipping point, it flips over basically, right? So this is actually a really cool universal phenomenon. I think it plays into a lot of things downstream that we don't need to worry about with the way that the atom behaves as well, because the atom also naturally inverts its spin periodically. And as we know with light, it also does that too, right? Because light is obviously a depolarization and repolarization of the atom. So this is a really important general principle. But what I'm trying to point to is that perhaps the core itself is what's doing this dance, and not the actual Earth as a whole, right? So if you have a solid core, it's sort of inside of some viscous underlayer. It's maybe ever so slightly lopsided. I don't know. It's just not perfectly uniformly dense, right? Perhaps it's quite easy for the core to periodically invert, which doesn't change the motion of the Earth on balance, but it does carry that imprint of the pattern of the magnetism from before, which means that all of a sudden the magnetic imprint of that core is inverted and opposite that of the flow of the material. And it might have the ability to actually drag that material magnetically in this manner and get those eddies going in the opposite direction eventually.
So I was kind of right.
Yeah, yeah. I mean, and I honestly think the scientific community is in various stages of acceptance about this. We haven't witnessed an actual pole reversal ever before. So to get back to your question, Ezra, about like what's this going to lead to when the pole does reverse? Well, the pole's wandering really hard right now. And there's been some indications that there has been some tumbling of the core itself. These are all very difficult things to say about the interior of the Earth. But we do know that the pole's wandered several hundred kilometers, since the early 1900s, since we've been tracking it. So a lot of people think that this reversal is actually very, very near to occurring. The good news is that we've seen in the record the pole reversal happen many, many, many times. And we don't see it associated with any widespread catastrophes, right? There aren't, huge earthquakes or anything like that associated with this banding structure of the pole reversals, which kind of, I think, to most people, me included, indicates that it's something internal that's changing rather than something external. Yeah, Max.
But could it I don't really understand this that much, but could it cause some kind of disturbance to all technology on Earth?
Well, that's another question altogether. Yeah. So I mean, the geomagnetic field is actually extremely weak compared to, say, a bar magnet, something on your fridge. So, in so much as the magnets on your fridge aren't destroying your technology, now it's really big on balance if you were to take the whole thing as a whole, right? But in terms of competing with individual actual magnetic effects on Earth, I'm not seeing that it will really be that big of a deal. I think there's a lot of money in freaking people out and making YouTube videos about it and stuff like that. I know one of these guys, and I would love to just get in a cage fight with him or something, but I'm getting too old for that. Yeah.
Isn't the magnetic field, as the video on the right is kind of showing, isn't that why we have the auroras?
Yeah. Yeah.
It's because it's
Well, it involves the solar wind too, which I'm going to get to in a second.
it's a little weaker there, so there's more radiation that gets through.
Yeah, so if you look at my map here, right, my simple circuit, you see this flow of the atomic material that kind of coaxes everything in through the center of it, right? These are literally just the surfaces of the atoms in their extended form, just all kind of turning as one unit. So they do kind of usher in anything, very much like a vortex that's just pulling stuff into the center. So yeah, we'll get to that. I want to talk about the solar wind a little bit and what the heck those auroras are all about and everything. We do,
So
yeah.
it's kind of like a donut. With
Yeah.
a very tiny hole at the poles.
Yeah, that's a good way of thinking about it. Yeah, it's a good donut. It's true. Yeah, it's more like a vortex. It's kind of pushing and, yeah, it's just sort of pulling in. Now it's going to pull things in. Basically, it's very easy for any charged system. So if we have individual atoms that are charged, they're going to be really susceptible to these magnetic field lines, right? So other magnetized atoms, so permanent magnets like iron and stuff like we talked about that are imprinted and have this impression, they're going to be susceptible to this, but also charged particles are susceptible to magnetism. So I'm not susceptible to magnetism. I'm neutral on balance. So are you. So is much of the stuff in this classroom. So I could walk up to you with a huge magnet and it's not going to deflect you or anything, right? Yeah.
Just because you said the word vortex, it reminded me of it. I drive on I-5 a lot and I pass by the Oregon vortex a lot. And
Oh no.
there's like a lot of talk about magnetism,
Yeah. Yeah.
like force.
Yeah.
I was just kind of curious.
Yeah, I mean, I don't want to slander any of these people. I don't know. My parents live in Sedona, Arizona, and there's vortexes all over the place. I don't think yeah, I'm not sure that it has any basis in anything we're talking about necessarily. I mean, that's not to say that these aren't like special places on Earth or something. They might be. I just don't think that we're talking about the same thing. That's all. Now, look. People like your body is like. Have you guys ever? Anybody ever had an MRI before? Nice. So I haven't, but it's a really cool technology, and actually one of my mentors helped develop that technology. It's really cool, but you're basically, in some sense, you are applying really really strong magnets to the molecules in your body, especially the waters, right? And so you can actually induce a magnetic field by applying magnets to molecules that, all these molecules do have some lopsidedness of their charge distribution. So you can make an argument that it still is electromagnetic at the end of the day. But, on balance, you're neutral. So if we just put you in an MRI machine, you're not going to like fly against the wall of it or something like that. Yeah.
Question, I know that you're not supposed to like, if you have metal in your body.
Yeah, well, could be magnets.
Issue.
Right. So not all metal is going to be susceptible to magnets, right? Because some of those metal, this model that I've given you guys so far is a very simplified version because I'm only dealing with one electron in this, right? One electron, so one simple pattern on the surface of this atom. It's a hydrogen, basically, right? And I've made a wire out of hydrogen, which is ridiculous, but it still serves the purpose of what I'm trying to show here. In some of these metals, we're talking about dozens and dozens of different surface features, like the spin pattern that I showed you, but lots of them. And some of them construct and interfere in different ways that it means that they can't really be influenced by external pressures magnetically for whatever reason. There's something structural about some of these atoms and some metals. I can't think which ones.
Titanium.
There you go. Yeah, which ones aren't though? There's some that aren't, right? I don't know. Sometimes though, I couldn't think of one off the top of my head, but I know that some metals you try to stick a magnet to and it's just like, it just falls off, right? So the way I'm looking at it, it probably has a lot to do with the electron configuration. I guess that's the way everybody's looking at it, but the way I'm looking at it is it probably has a different surface pattern to the flow of the material on its surface, which is just locked in place. It won't be rearranged no matter what. It doesn't have the same degrees of freedom. Yeah.
Yeah, titanium isn't magnetic.
It is not. Interesting.
Non-magnetic, so is lead.
Does it get hot though in magnets? Because you were saying titanium is a problem for MRI machines.
Well, my mom had a titanium plate in her head.
Yeah. Oh wow.
And so, yeah, it's kind of an issue sometimes.
Could she have MRI?
With the imaging.
Yeah, I can mess with it.
That's true.
Yeah, she had to have it. But yeah, I know that titanium, I think, is one that's okay.
It's okay.
Yeah.
Yeah, I mean, you wouldn't want like a big steel plate in you. There's been some horrific stuff where like untrained people walk into MRI rooms, with like there was a guy who recently, not that recently, but saw on the news that he had one of those oxygen tanks for the patients, and he went in while the MRI machine was on and he got like sucked into the MRI machine and pinned against, I think he died actually. He got pinned against the wall of it.
Yeah, I know about that. Yeah, and then the two, choked him.
Yeah. So they're really, really strong magnets. My point is that this is all quite interesting, but my point is mainly just to impress upon you guys that you have to be either a magnetizable ferromagnetic metal or you have to be charged for a magnetic field to really matter to you. All that nasty stuff that's coming at us from the sun, that really high energy wind stuff, is highly charged. And that's why the magnetic field shields us from it. So let's just talk about that. We're basically at the point. This is showing, I think, the drift of the magnetism. It's not a very good picture. All right, so let's talk about the solar wind, because we'll get way more into this next semester. I don't have time to go into all the fun stuff about the sun. But the solar wind's kind of interesting because, in some sense, I'm making the argument for you that half the reason we're able to even be sitting here having this conversation is because this magnetic field shields us, or this magnetic character of the Earth itself acting homogeneously as a giant electromagnet with a reinforcing, amplifying solid core of nickel iron, right? Because we have that beautiful system, for whatever reason, thank God, this really gnarly wind that's flying off the surface of the sun is shielded from us. So what is this wind stuff? Have you guys heard of this before? It's pretty bizarre, right? So I don't want to get totally deep in the weeds on this, but you know, there's a couple ways to look at this. So the standard picture, and this is actually a picture that was developed in the 1950s by this guy named Eugene Parker, is that, well, the standard picture of the sun in general since really the early right around that time period, maybe a decade earlier, is that the sun is kind of this giant conductive gas ball thing. And what's happening is that the heated gas at the surface of the sun, by the way, the sun doesn't actually have a surface under this model, which is a whole other issue we can deal with in a second. But somewhere around the place where we see this optical illusion of the surface, basically this gas is really, really hot. And because it's hot, it's expanding. Because it's expanding, it's moving away from its center. And the force of gravity falls off a lot faster. Gravity, of course, falls off this inverse square law, but this gas's thermal expansion falls off slower. And so at some points, the expansion of the gas, because of its heat, wins out over the gravitational pull, and some of it escapes off into the distance. That's kind of the standard picture for this solar wind stuff. And then, of course, the fact that there's all of these really intricate magnetic features at the surface of this, at the optical illusion of the surface of the sun, leads to the charging, of these individual atoms as they're flung free, basically. Another way to look at this, which we'll do the full justice of next semester, is that the sun really does have a surface, and that it is some sort of condensed form of the same elements. It's some sort of condensed form of hydrogen and helium. And that where you have an actual phase change at the surface of the sun, let's say from liquid to gas, that you have the natural tendency for some sort of evaporation-like process to take place. And then the same basic model takes place after that, except for the evaporative process involves a kick, so it has some jump to it from the start. The bottom line is, at the end of the day, we got these really, really light and highly charged atoms that are flying away from the sun and accelerating on account of the fact that gravity is playing less and less of a role in the picture. The sun also, this magnetic dynamo that we have in the Earth, the same thing is playing out with the sun, except for the whole thing reaches all the way out to the very edge of the solar system, actually. And it reconnects back through the top of the sun, which is really, really crazy. You can imagine the donut of the sun actually going way beyond all of the planets and then coming back. They call this thing the heliosheath. So there's this whole magnetic structure that's accelerating all of these wind particles. We'll just call them wind particles for now. But they're basically just charged lightweight atoms. And they're rocketing past us. And if we didn't have this nice magnet to eat all of these for us and direct them in towards our poles, then they would rip our DNA apart, and the wind would. And it would be, we wouldn't make it very far, probably, down that evolutionary pipeline. So you can see that, yeah, as those charged particles fly in, they're actually directed into the poles by our own magnetism, which is fantastic because it saves us, but it also gives us these really beautiful auroras because those really fast-moving wind particles collide with our atmosphere, and you get these beautiful electric reactions where this process of ionization takes place, and you get the emission of light as a result of it, and that's how we get these beautiful, green and magenta auroras and all of this stuff. Yeah,
It's be called more like also cosmic dust, referred in that way.
dust.
Legitimacy in this theory. It seems like there's really not dust particles. It's kind of like wind and light.
There's a lot of dust in the atmosphere. There's a lot of dust in space too. I'm not sure. I mean, to the extent that perhaps there's little pieces of metal and stuff that also get ionized in the atmosphere and also lead to some of the colors. So, some of the more standard colors are attributed to oxygen and nitrogen in the atmosphere, which is what most of the atmosphere is to begin with anyways. But yeah, maybe some of I've never seen one of these things. Have you guys seen them before? These auroras?
Yeah.
Yeah, you lived in Alaska. That must have been awesome.
Practically. So did you?
Wow, that sounds amazing. Did you see it? What kind of colors did you see?
Mostly green.
Green, yeah.
But mostly green.
I think the green is the oxygen, if I'm not mistaken. Maybe it's the nitrogen. I'd have to look it up. But those are the two main gases in our atmosphere. But there might be some other traces of things that come from, again, little trace elements up there.
Yeah.
So, party in the hallway. What else do I want to say about this? Yeah, I guess that kind of leads us neatly into here. What you guys have any thoughts about all this magnetism, solar winds? Is there any confusion about any of these features right now? Yeah.
No, but what is? I haven't heard of krypton gas.
Krypton. I think I don't know. What can we say about krypton? It's on here somewhere. There it is. It's a noble gas. It's number 36 over here on the far left side, but I can't see it.
Oh,
I really hope I don't rip this thing down. I knocked a clock off at the beginning of class one semester. It was really bad. Because it gets crooked. You just really want to fix it, right? So don't touch it. Any more magnetism questions? Oh, God. All right, I'm gonna have to close this door. Actually, does anybody want to get the door for me? Thank you, Ezra. Appreciate it. Of course, they'll be quiet as soon as he goes and does that. Any thoughts? Magnetism, the Earth's core, spinning core, inversion. Yeah, let's make sure we dust up all of this. Yeah. Yeah.
What would you say? Did you say exploding like our DNA would just?
Well, yeah. I mean, if you just walk out into the solar wind, you're toast, pretty much. Like, you'll just what was it? Indiana Jones and the Temple of Doom. The guy's face melts off or whatever. Like, that's gonna happen to you if you just go and stick your hand in the solar wind. It's really gnarly stuff.
I hope that's built into kind of like.
It is. Actually, the more you learn about our planet, the more, especially when we look at all the other planets, the more you realize this place is really special, actually. It's weird, actually, how special it is. Which might be why it's so hard for us to find life. So, another thing, so at this point in the course, it generally would have us talking about origins of life, stuff like that, search for life on other planets. I'm going to hold off on that because my wife is also a PhD biologist. She's way better than me, and she's really good at talking about origins of life stuff. She's out of town for the next week or two, so I'm going to push that discussion back and have her come in and talk to you guys about it. But yeah, it's really magnificent. So in addition to us being in this perfect place for liquid water, we have this incredible shield that keeps us safe from our sun, which is really rare because you look around the rest of the solar system, nobody else, none of the other rocky planets have anything like this, right? So it's a pretty special situation, yeah.
I have two questions. One, if all the solar wind is being directed toward the poles, does that mean that that's also why there's more radiation there? More
radiation. Yeah, it probably is. But it's dark. Yeah, half the year is pretty dark. More radiation. Maybe more high energy radiation. Is there more radiation on balance up there? Probably. I wouldn't be surprised. Yeah. But I mean, the atmosphere is going to do a pretty good job of a lot of this. Yeah.
Yeah. The other question I had was about how magnetism affects gravity,
Mm.
because I've heard this explained to me about Mars, that one of the reasons that it's there is that it doesn't have the gravity to hold down the or gravity, something it could be
It's atmosphere.
but something like that. Why it doesn't have an atmosphere?
Yeah.
It's not able to hold.
Yeah.
It just sheds off.
Yeah.
Is because it has its core cooled, went solid, and now it doesn't have a magnetic field or a strong one.
Yeah, I think that the argument there, so there's a couple of pieces there. Gravity and magnetism, we should talk about that. With Mars, the idea is that there's a number of ideas about why it cooled, and we'll get to that when we get to Mars. Because Mars doesn't have this really nice magnetism anymore, at least, it seems like it may have at some point. Its atmosphere wasn't protected against that wind, that solar wind. This is another piece of the puzzle that's really nice. So I mentioned that it's really great that our DNA is protected. It's also really great that our atmosphere is protected, because one thing that stars love to do is evaporate the atmospheres of planets. And I think I mentioned this earlier. Oh, I did. I mentioned this earlier today when we were talking about the expansion tectonic stuff, and the mini Neptune possibility of the past. By the way, the main reason nobody wants to take the mini Neptune thing seriously, I forgot to mention this, it's worth mentioning. It should take a really, 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 really long time for that to happen. Unless, we're one of these Neptunes that gets stuck right next to the sun, and we do see these. They're called hot Neptunes. Unless we were one of those and then our orbit changed, there's no way it could have happened in the 4 billion years that the scientists have allotted for Earth's entire history. 4.5 or whatever it's supposed to be. However, and we'll talk about dating of the Earth eventually, I'm not so sure that that's the whole story of the Earth, is this 4.5 billion year thing too. So my point, though, with the photo evaporation is that we see these planets that are really close to their sun, and they're losing their atmospheres at incredible rates. They're just cooking off their atmospheres. And so if you don't have a really good magnetic field, or if you're too close to the star, but even if you're not that close to the star and you have no magnetic field, it can strip this wind can strip your atmosphere away really, really quickly. And gravity just can't hold on to it at the cost of it being stripped away.
I wonder if something else that could cause a Neptune to lose, to no longer be a Neptune, right? Is if it's impacted by another body of a similar size.
Yeah, maybe.
Because I've heard that theory posited several times for Earth and the moon.
Right.
There's been more evidence of that. So that could be it. Could have been that impact.
Yeah, absolutely. I mean,
Yeah.
there's a number of ways that you can imagine that, and we're going to keep playing with this idea all semester long, because I think it's really, really important. There's really two roads here that are starting to emerge in this class. We've kind of reached this point where there's really two paths to explain everything. One is this story where everything kind of formed looking exactly like it looks today. This is kind of the one that's in your textbook. It all congealed out of this same thing of swirling gas and dust. The star happened at the center. There was some leftovers, all the planets, moons, everything basically formed. There's a little bit, I'm smoothing things over. There's a little bit of motion and some changes, but for the most part, things kind of looked more or less the way they do today. So that's a very uniformitarian approach to the past. There's also a very different approach to the past, which I see as gaining a lot of steam at sort of the underground of what's happening, which hasn't quite made it to the textbook, which is a more metamorphic story, where planets change their shape and size, and everything changes over, the course of eons, perhaps, is one possibility, or through black swan events, right? Through weird stuff. Orbits change. You're close to the star. You change your appearance. You lose your atmosphere. That decompresses your surface. Your crust cracks. Things happen, right? These things that are very difficult. They're not uniform, right? They're not these uniform processes that just unfold nice and linearly. They're these kind of stepwise events. So there's basically just two kind of stories that are starting to emerge here. And we're going to look at the evidence really for and against both of them throughout the rest of the course, because every single planet has kind of a story that could go on either path here. That's why I called this course the evolution of the solar system, because I think evolution is, or metamorphosis or something like that is perhaps a better way of thinking about it. But yeah, that's not necessarily the popular way of thinking about it just yet. Depends who you talk to, I suppose. Magnetism versus gravity. I wanted to address that. So magnetism, first of all, you can beat gravity pretty easily, right? You guys stick things to your fridges probably with magnets all the time. Gravity doesn't get a say for the most part, right? Magnets are really, really strong. And in fact, electromagnetism just in general is orders of magnitude stronger than gravity. Gravity is super, super weak, right?
Yeah.
Now, why might that be? Well, from the way that I've illustrated this atomic situation for what actually magnetism is like a very cohesive patterning of the motion of the surface of the atoms. In other words, they're all kind of working together, doing the same motion, right? But most of the universe isn't a magnet. At least most of the room isn't a magnet right now. Let's start with that. I think that actually the universe is full of ionized conductive things, but let's not get into that. The room is not a magnet on balance. So the way that I think about gravity is that it's very much similar to magnetism in that the atoms are affecting they're affecting their surroundings based on their extended structure. But with gravity, it's sort of just the baseline chaos, right? Most of our atoms, our shells, are not doing the same thing as the ones next to them. There's no cohesion in the motion, right? And so you still have some interaction with your surroundings through the extended architecture of the atomic surface, but it's just not patterned, right? And so it just results in this kind of network tension amongst all of the atoms in the room right now. You're particularly oriented towards where most of them are, which is in the floor, right? And so you're sort of gummed up and you're sort of sticking to the things where most of the atoms are, which is underneath you, but it's not patterned like with magnetism as much. So gravity tends to lose for the most part when it comes to magnets versus gravity. Also, those hover trains they got in Japan, stuff like that. Probably seen that. Pretty cool stuff.
Maglev.
I keep wondering when we're going to get our cool train system out here. Really nice to go visit my family down in San Francisco and just jump on a train, wouldn't
The
it?
government decides it has enough money.
Well, you gotta just.
A few years ago, Elon Musk was working on a lot of maglev stuff
Oh.
trains for the U.S.
Yeah.
So was the state of California. Both projects fell through because America is not Japan.
Well, yeah.
It's larger.
Well, it's a lot of like NIMBY stuff, right? Like people don't like the California stuff is people don't want to put the train lines through their own backyard, right? They're like, no, it goes in his backyard, and then people lobby and.
It's also just that America's really big. The environment is so big, obviously, it goes from coast to coast, and so the environment changes so much that it would be impossible to get for a government with our current funds to be able to do that.
Let's not say impossible.
It's just really expensive.
It's expensive. I mean, but there's a lot of everything. Yeah, I don't know. This is too big of a conversation.
Unless it's the military.
I feel like
They're
one
covered.
coast-to-coast train is kind of ridiculous, though.
Like a single one.
Want that to begin with. I mean, like, I'm sure, like, it would definitely make travel easier, but the amount of changes, like you said, in the environment and the, like, stuff, I don't know why we would think that would be a good idea.
What do you mean? What's the downside?
Well, just like, going over mountains or whatever.
Well, you go through mountains.
You could go around them, maybe. I don't know. There are coast-to-coast train lines. Is the thing.
Yeah,
They're just incredibly inefficient, and
America.
the tickets aren't subsidized. Like look, the airline industry is not like it doesn't cost the price of airline tickets has nothing to do with like the cost of getting on an airplane. It's all standardized and subsidized by government petroleum issues, and like the cost doesn't necessarily reflect the true cost of doing anything.
The price doesn't necessarily equate cost.
Yeah, the price doesn't actually necessarily affect the cost. So if the government wanted us to subsidize trains, they could do it. But there's the automotive industry, which is lobbying to fight back against that. There's the airline industry. These are like huge, huge powers in Washington, and they're not really interested in seeing things change. And you know, I was just in Europe this summer, and the trains are suffering from the same thing because Europe used to have a great train system. Everybody traveled by trains, but the airline industry has basically lobbied all of the different governments so that it's cheaper to fly on airplanes than it is to travel by trains, which is sad. And they have the train infrastructure. It's just you can't get a train ticket for the price you can get a plane ticket.
I do think it's funny how there are the American and your like car companies that are trying to get rid of public transportation because they think it's going to eat into their money. But if you look at Korean and Japanese automotive companies, they just make the public transport. Hyundai, they make shipping like large transport ships, send shipping containers.
Yeah. Yeah, I don't know. I don't know how that all played out. I mean, it was a really radical decision back in when was it the 1950s to build these huge interstate highway systems. That was a really radical decision.
We didn't have the money, and we still haven't completed them until the 70s.
Yeah, they're a really wild project. There's so many layers to this. I don't know. I can't. There's so many layers. All right, let's talk about the atmosphere though, because we need to move on. We need to talk about the moon. We need to talk about.
I love the moon.
We need to talk about impacts in general. We need to talk about how old this thing is. So some dating ideas about why we think the Earth is as old as it is, or why we don't think it is, perhaps. There's a lot to talk about. I want to make sure we finish everything to do with the atmosphere today. The last piece of the atmosphere that we really need to talk about is really cycles of weather and pressure and things like this, which are kind of interesting. Yeah, so this is the atmosphere, by the way, before I move on from it. You can see almost all of it is nitrogen by a long shot. There's quite a bit of oxygen too.
I'm surprised there's that much argon.
Yeah, well, whatever argon is, right? I don't know if it impacts us or not. It's an inert gas, right? So all of these guys on the right side of the periodic table, which I can't really show you guys. No, I'm not gonna be able to move it. They're all quite inert, so they don't really react with anybody, which is nice. So all of these gases, for the most part, are non-reactive. Of course, hydrogen will react sometimes. Helium, these things do happen, but not that reactive. So this is our atmosphere for the most part. Where did it come from? That feeds into our bigger discussion too. I think maybe this doesn't warrant its own discussion, but it seems like I think I pulled this from your textbook. First possibility, the atmosphere formed with the rest of the Earth, which I'm like, okay. Now, of course, they go on and say it accumulated from the debris left over from the formation of the sun. Maybe that's one possibility. If the Earth is some metamorphosed version of something very different, then perhaps the atmosphere is also a remnant of that. Second possibility is that it was released from the interior through volcanic activity subsequent to the formation of the Earth. So you guys probably, let's see, volcanic eruptions. What's that stuff that comes out of volcanoes? Yeah,
A lot of gas.
there's a lot of gas, actually. And what is that gas?
Yeah. I mean, I know a lot of it's carbon dioxide, but
Some of it is. Not a lot, though. Some of it.
isn't it sulfur?
It's water. So maybe some of the atmosphere, maybe some of the water, maybe some of the other content. Of course, water can be broken up into oxygen and hydrogen too through electric processes. So, maybe some of the atmosphere did arrive through volcanic activity. Certainly some of it arrived through, it's still happening to this day, right? There still are volcanoes going off all the time. Yeah, we got one right in our backyard, right? I guess it's supposed to be sleeping, or is it supposed to be extinct? This Mount, what's this one called? McLaughlin?
We
Yeah.
also have Crater Lake, which
Crater-
is also a volcano.
Very, very old, thought to be extinct. Yeah.
I mean,
Um,
it's not technically.
It's not technically
the
extinct.
Wizard Island is still technically like active. Like,
Interesting. I didn't know that.
the original volcano, it's like a baby volcano
Okay.
sequel.
It's just sort of just puttering around, not scary.
Yeah.
All right. Well, so that's the second possibility. The atmosphere came from volcanoes. Third possibility is that it was derived by impacts with comets and asteroids from the outer part of the solar system. This is kind of the really old and withering explanation for where the oceans came from as well, which we may have touched on in the past.
Which always seemed absurd to me as a kid.
That one's just cringe, in my opinion. I remember hearing that when I was like 10 years old. And you guys have heard this before too, right? The oceans came from comets or something. You guys, they don't really say that in school anymore. Okay. The oceans. Yeah, that was the standard story when I was a kid.
The comets had water and then
Yeah,
they crashed.
yeah.
Like
It's a lot of comets.
They had ice and they crashed.
Yeah, they were icy comets. They smashed into us.
Oh,
All right. Well, at least that's possibility three out of three from the textbook. Still a lingering possibility. We'll let it pass for now. So yeah, those are the options. We do have this beautiful atmosphere. There was a really beautiful paper that came out in Nature back in 2022 that looked at the Earth as having basically formed its oceans from a very primordial, thick hydrogen atmosphere, where the hydrogen was interacting with the rock. Because what is rock, by the way? Somebody mentioned it earlier.
Granite.
What is it, though, fundamentally in terms of elements or molecules?
It's a mineral.
Mineral, what's the most dominant one?
Quartz.
Which is made out of?
Oxygen.
Silicon.
Yeah, silicon. So silicon dioxide is basically quartz. Now, so that means that what is silicon dioxide? It means there's two oxygens stuck to a silicon, right? So there's plenty of oxygen. If there's a primordial hydrogen atmosphere in the early years of the Earth, whatever that means, then they can interact and make a lot of water together. We know there's tons of water bound up inside of the minerals today underneath our feet. So some estimates are as much as 7 times the ocean's worth of water is just embedded into the minerals, literally bound to the individual minerals, the individual silicons or irons or nickels or whatever, magnesiums. So lots of ways that we could have ended up with this atmosphere we got. Thoughts before I move on from that?
It's very pretty.
The atmosphere? It is very pretty. I totally agree. Got a lovely blue glow. It's prettier. It's really pretty some mornings. The sun comes through it. So the atmosphere, again, protected by the magnetic field or the magnetism of the Earth, maybe a better way of putting it. There's several layers to this, actually. There's a couple of other little features that are worth mentioning. The ozone. Textbooks love to talk about the ozone hole. Do you guys know about this? When I was a kid, this was a big deal.
Yeah.
Yeah, so there's ozone is this weird oxygen tetramer, so it's just 3 oxygens stuck together, and it acts like a really nice absorber. It something about the shape of the 3 of them together absorb ultraviolet light really, really well. They're like little shock absorbers for ultraviolet light, which is good because ultraviolet light is also quite damaging to life on Earth, ultimately. It's also can resonate with your DNA, and that's not good. Too much of it isn't good, I should say. So sometime in the 80s, people started studying the ozone in the atmosphere, which is another one of these protective mechanisms, and they discovered there was a huge hole over Antarctica where the ozone was being depleted. And they chalked it up to reactions with chlorines and bromines, which are another column on this periodic table that it's this second from the right over here. they happen to interact with this, and it destroys ozone. So these chlorines and bromines. Well, they figured that where is all this chlorine and bromine coming from? They realized that since the advent of the 20th century, people had been using chlorines and bromines as what?
Well, what happens when there was chlorofluorocarbon
Yeah,
and just like in the hairspray
yeah,
and like, aerosols,
yeah.
and also in like the packaging that we would use.
Interesting. I know about the packaging, but yeah, it's used in pressurized gases. It's used primarily in as refrigerants. So the way that, of course, air conditioners and refrigerators work is by evaporating or condensing gas in these tubes, therefore changing the balance of heat, right? Because you release heat or you have to apply heat, suck up heat in order to do work on the system. And these guys do it really, really well. They have really good thermal expansion coefficients or whatever. They're basically able to do this heat transformation process really, really nicely. So throughout the 20th century, everybody loved these chlorofluorocarbons, and there's bromide versions of this as well. Everything in that column, it turns out, works really well. I forget what that column has a name that I can't recall. Anyways, the scientists were like, it's those things that are doing it. Those things. So they had this big conference, what did they call it? The Montreal Protocol. This was in 1990. They banned the use of these chlorofluorocarbons. And it was one of these huge moments, like the hole started to go away. Everybody like patted themselves on the back. Everybody was like, yay, science. And that was good and everything. But this is actually since 1979 all the way to 2022. This is the extent of the ozone hole since then. It's still there. It's actually waxing and waning. Depending on who you talk to, maybe it's on average a little bit smaller than it used to be. It's kind of hard to say. It's an interesting story because the reality is we actually have removed a lot of these gnarly chlorine and bromine molecules from our atmosphere as a result of it, which is probably a good thing. I'm sure that they're really toxic to our bodies in other ways. I don't have any reason to believe that, but I imagine that huffing CFCs would probably kill you pretty quick. Yeah.
Ozone is actually also one of the most toxic naturally occurring gases to life.
It is really gnarly stuff. Yeah, we used to clean like surfaces with it when I was in grad school. Like if you wanted to clean a piece of silicone or something that you were trying to put in under a microscope, you would put ozone on it to basically wipe everything out. Yeah, it will kill stuff to death for sure. So I don't know. It's just kind of a funny little story. I don't even know what to make of it. I just think it's really interesting how we do this sometimes, where we convince ourselves that if we just deal with this one little factor, everything else will be fine. But it's almost never the case. Yeah.
The colors exactly working on them. Like, what exactly do they represent? It's just green.
Blue's the whole.
Blue's the whole. Yeah. Red's like the maximum extent, I guess.
And green is, I think.
Oh, red is like the biggest one.
A lot of it, yeah. So there is these.
Like that.
You might wonder, like, why is this hole over Antarctica, right?
The poles.
Which is a good question. There's these really interesting polar vortexes, which I hope we'll get a chance to look at here in just a second. I have a really cool map of the Earth that's kind of interactive. You guys can take it home with you and check it out. But there's something about the spin of the Earth which results in these vortexes that really tend to just sort of like if you go to the river and there's like some foam on the surface, it gets caught on these rocks because there's these like churning vortexes basically around the rocks that just trap all this stuff. I think it's the basic idea is that a lot of these bromines and chlorines get trapped down here at the bottom. Anyways, we cleaned up the atmosphere from our own man-made CFCs, but hole is still there. So maybe it had nothing to do with them in the first place. Maybe it will be repaired any day now. I have no idea what's going on. It's just a very strange story on balance. And it's become very politicized. Maybe nobody cares about it anymore. It was a big deal when I was a kid.
About CFCs. And why?
Yeah, I don't think anybody cares anymore. Probably because of this, because it's not like the triumph story that we were hoping it would be. I just think this kind of, in some sense, it sort of reflects this idea that like people like to focus on like one thing. They're like, if we could just get rid of this one molecule, like everything will be fine. You know, if you just eat vitamin C, like you'll live forever. Like everybody, like humans really want these magic bullet solutions to everything, and it's unfortunately almost never that simple.
It's a culmination.
Nature is extremely complex. Yeah, there's always many factors involved in anything, right?
Yeah, you see this with how people talk about history too.
Yeah. Oh my goodness.
History
Don't
is
get me started.
random set of events that seem completely unrelated, but somehow affected each other.
Yeah, that's a great point. Because history is just like that, where you can listen to someone's presentation, they can be very sane and rational, but then then you're like, but what happened right before that? And then you're like, oh no, this thing started back then. And then the further you go, and then there's all these people involved and all these interests, and yeah, reality is extremely complex. So we're gonna finish this atmosphere today. I got 5 minutes left. What can I do in 5 minutes? I want to show you guys a map that's pretty cool. Maybe we can talk about lightning a little bit at the beginning of next class. I'll come back to it because it's quite interesting as well. This is pretty cool. Do you guys know about earth.noschool.net?
Oh,
This is
yeah.
pretty rad. If you don't know about it, I would recommend you just go home and play. So that's the website. It's just type into Google or whatever, earth.noschool.net. You can get this browser. I just pulled up Hurricane Melissa while I was getting ready for class here. It's really cool. So you can basically see the not only the wind patterns, but you've got this whole shelf to navigate. You can look at different particle amounts. You can look at temperature. You can look at CO2. You can look at basically anything you want. And then the other cool thing is that you can look at the height at which these different wind patterns or whatever system that you want to check out is playing out at. And this is really cool because if you notice, you probably can't read this from here, but the height is listed in terms of HPA. Why do they list the height in terms of HPA?
Hectopascals? Is that what it?
Yeah. Why? Why is it in units of pressure?
Because the higher you go, the less pressure.
Yeah, exactly. And this is actually the way that airplanes know, well, at least one of the instruments they use to know how high they are, right? Because pressure is directly dependent, and that was kind of the picture that I'd showed you guys earlier, was that the pressure is directly dependent on your height. And so if we go really high up to the upper atmosphere, look at that. The wind is all basically quite laminar in its flow.
It kind of looks like a gas giant.
Yeah, it does actually. It's quite laminar in that way. And then if we go down, let's go to the other hemisphere. We can see that polar vortex down below, right? So there's kind of a swirly thing down there. Actually, it's all quite interesting today.
It's doing something weird.
It's a little bit weird. Something weird's going on. So anyways, this is a super cool platform. You can just get lost on this. It also helps you to maybe, when we get some weird weather up here in Oregon, you can go and, oops, where are we? Where are we here? You can actually kind of track down and start to make sense of why things look so strange. I'll go back down to where we're at here, surface level. Oh, there's like a little bit of a vortex up there by Alaska too, which is kind of cool. Anyways, you guys can play with this in the meantime. All right, well, at the beginning of class next time, let's deal with atmospheric phenomena like lightnings and storms and stuff like that. Those are probably worth mentioning. Otherwise, then I want to talk about impacts and asteroids, and we're going to get to the moon eventually, and then we'll move off the Earth and check out the rest of the solar system. So,
I love our moon.
what's that?
I love our moon, Luna.
Yeah, well, it's perhaps very useful. We'll see. All right, guys, have a wonderful weekend, and happy Thanksgiving and all that.